Swayam Prabha. Digital India. Educated India.
So here you can see that the single point moorings, loading buoys and deep draft floaters. When we say deep draft floaters, we basically mean the draft is very high compared to the width of the structure. For example, in your spar, the draft is very high compared to your width of the structure. For example, in case of a spar, 30 meters, but then the draft will be around 120 or 90 meters, right? Okay. Okay, and so this is about the mooring design, but it doesn't end there. When you start a design, you have to analyze, you have to again make changes to your design. So it's an iterative process. So that's what we have been saying. And quasi-static, so the different mooring analysis exist: quasi-static, frequency domain, time domain. So this is what the industry practices. Again, in this time domain, we have the decoupled analysis, coupled analysis, right? Decoupled, coupled, right? So, but before we get in this time domain, it is important to understand the quasi-static analysis, because that is the very first step. When you have a floating structure, you put your moorings in place. Quasi-static, the word itself clearly says that it is not disturbed much. Your floating structure moves very slowly such that the line dynamics are not affected, right? Basically this point moves along with your floating body, correct or not? If that is going to, your floating structure is going to move, that is also going to move along with it, right? So it will create some kind of a whipping action. In reality, right, it will create some kind of a whipping action, but then if your floating structure is not responding to the environment and is going to slowly move, then you will end up having a quasi-static analysis can be done. So that will be the very first step, and then you can go on to do the time domain analysis. So the industry practice is the time domain analysis with the decoupled approach. So this is what the industry generally practices. The coupled analysis we generally don't do. The reason is it is cost, it is a very high computation cost. To solve a problem, it takes almost a week to complete, right? Whereas in case of a decoupled analysis, you do the floater motion, hydrodynamic analysis separately, and then you feed it. You already preset how your floating structure has to respond. You are already, without any moorings, you will do the hydrodynamic analysis, and then you feed it to the system saying that for a given wave the floater will behave this way, and then now you go on to connect your moorings. Now the moorings will actually, in reality it is not the case, they are all a complete system, correct, but we are separating them. We are dealing the floating body separately, and you are giving that hydrodynamic behavior to the structure that you are interested, right? And then when your excitation is set, right? So because since you are already programmed for your vessel to behave this way, right? It is behaving, and then you connect your mooring lines now, right? So this is primarily done to understand what is the extreme load that your mooring line will experience for that scenario, right? So this is what generally the industry practices, the decoupled approach. Coupled we generally do for the research activities and other things, but then if you are able to accelerate to get the result right, then this can also be adopted. So now the basic data input is that, so you need what is the type of floater that you are going to deal. So in this particular case we have the wake characteristics, what is the type, dimensions. We told that the floater motions will give the loading to the fair lead of your mooring line, correct? That is what is going to travel to your line, correct? So this wake characteristics and environmental loads, wind, wave, current, water depth, soil characteristics, and operational requirements. So sometimes you are very as said, for your drilling operations you wanted to have a very less excursion, correct or not? Because you go exactly to the site and your floater is there, and exactly you go to that particular location. For example, right, if this is the site and this is the place where you want to drill, and you will take your semi-submersible exactly to the top of that place where you want to create the well, then you have a restriction that how much this floater can move around, right? So we have some constraint. So in such constraint, has to be taken in consideration, right. So the excursion limit, and then the preliminary design, basically selecting the mooring type and the number, and also the mooring line characteristics, and then the mooring line arrangement as well. So how it has to be connected to your floating vessel and where it has to end. We start with the static analysis, then we go on to the dynamic analysis, then you do the design criteria. So this is basically, you can see that it is not complete, so it is going to be a iterative activity, correct. If it satisfies, go to the next step, or else you go on to change it. So that's what we mean. So the static analysis basically is to have a good understanding about what is the Fairley tension you get without any loads and other things, right. You just have a floating structure, you connect your lines to the structure and what is happening around, right. Dynamic analysis, so basically when we say it, you are subjecting your floating to respond to the waves, and then because of the response of the floater, how that is being transferred to your mooring line, right. Then we move on to check the design, because all items have a limitation. What is the breaking load limit, right. You will, when you purchase some item from shop, you actually know, don't apply more than this load, it will fail, right. The same thing for your mooring lines as well, you will have some limit. So by doing all these analysis, what we are trying is that whether it is within the limit or not, whether my item will be sustaining, whether it will be safe for the 20 to 25 years service life, right. So that is why we do this ultimate limit state, accidental limit, fatigue limit state, right. Once it satisfies all these, it is finished. But then, sir, whether it is an optimized outcome, definitely not, right. You need to, again, for example, if you are able to obtain a solution, it may pass all the things, right, but then it may not be cost effective. Again you need to go on to change some parameters, make iterations, again come back. So this is way it is generally done. So basically it's an iterative activity, right. Okay, so any questions? So now we will go to some derivation. We will, I think many are a little dozed off, so we will wake them up with derivation. Yes.
Did they consider the temperature gradient from the water surface?
No, they don't worry about. They are all rugged structures. All this chain, wire rope, the temperature gradient will not have any impact on the overall performance of your mooring. No. Yes.
Generally, how much does it cost?
I am not aware of the cost, but it's all huge in numbers. That too, when you say offshore mooring lines, right? Because it has to take care of the corrosive environment. So it is not just your normal steel. It is basically the galvanized steel, right? So all these things will add up. So it's an add-on to your existing items. So it will be very costly. Yes, Prof.
I could give you some numbers. Some literature said that more than 9 cost 40% of wave energy converters. And in 2019, I visited Hawaii. There's a wave energy test site. Some more than 9 fair. And they are in the process to repair and rebuild more than 9. It costs the water depth not that deep. And from 30 to 8 meters, I don't know which one is fair. It takes them $2 million, US dollars. So give you sense how much it costs.
Sir, also like if it is FPSO means the amount which you are putting is like worth it because FPSO itself will be a huge number and the mooring lines will be less.
So again depends on whether
like point observers, let's say I am taking a point observer, it will be small, right? So for that itself the mooring itself will be more cost or
Yes.
can we like make it more
that is true. Actually, for a couple of say for example, it is like the product value may be very less, but the courier itself will cost you very high, right? The same way for many of the items offshore, the product it will be around 50% or maybe closer to that itself, right? So that is how it is. Yes.
What are the materials they are using? Did they using any carbon fiber or?
Carbon fiber, no, we have not seen. Mostly the chains, wire ropes, polyester ropes. If the water depth is very high, polyester ropes, because they will be negatively buoyant also, because that should not add any weight. Right? The primary aim of going to the polyester ropes and other things is that if you just leave it in water, it will float, right? Whereas in case of chain and wire rope, it is not that way, right? But the disadvantage with the polyester ropes and wire ropes is that the stiffness properties will change over a period of time. See, as we said, for 20 to 25 years it is going to be there, right? So during its time it will be going for extension, right, elongation, and again coming back to the place, right? So constantly this is going to act. So after some time the extension, it will not revert back to the total length, right? For example, you have some bodies, right? So if you keep on applying the load, after some time, even if you leave the load, it will not come back, it will be there only. So you need to adjust your winch tension. The fair lead, when we say it, basically you have some kind of a winch at the top, that is what is going to, little bit adjustments will keep happening. Yes.
What is the recent research trend in this mooring aspects?
Mooring aspects, coming back to the floating wave energy converters, so the moorings that is generally adopted for your oil and gas platforms, that is not exactly the same way it is done for that. So for example, you will have some kind of, so let me put it here. So you have your, let us take this your floating wick, right? So we don't, so as of now what we told, there will be a line which is running, correct? But then we don't do it that way, you will have some kind of a buoy, right? And then you will have it this way. So you are basically detaching the loads that is transferred from the wick to the, this one. So basically you are disconnecting the load transfer from, because the moorings will try to restrain it, right? It will start responding. So you don't want the response coming from the mooring. So you want to decouple it, you want to remove it, right? So that is the reason we will have some kind of a buoy, right? So that it will almost kind of a horizontal connection comes in picture.
What about that direction, sir? Like,
So direction, see, if you ask, that's a very generic question. For example, for a given site, so first thing is you will get a rose diagram, correct? You might have seen the rose diagram. What do you understand basically? In which direction, what is the most probable wave height and what is the occurrence of that, all those things you will get it. So based on that, things will be aligned. So there is no direct straight answer, right? All these things are site dependent activities. So you need to have extra data, right? Meteorological data, then which also includes these items. So based on that, they orient in such a way that it will take in considerations.
General span of mooring, how much lifetime?
See, whenever you have, so that is why we have this fatigue limit state. So when we say fatigue, so you carry out the fatigue analysis. Basically fatigue limit state, you mean that you are going to do a fatigue analysis, correct? One is, I am going to stretch it to the extent, what is the load that it will take to failure, that is extreme analysis. The other is a fatigue analysis, basically you are going to apply cyclic loading, right, for 20 years, sometime this side, it is going to be very cyclic in nature, right. For fatigue life of the subsea flexibles or something, the factor of safety has to be 10. So which means that if your service life is 20 to 25 years, right, minimum 250 years your fatigue life should turn out. When you carry out the analysis, if your fatigue life is more than 250 years, that is pass. If it is less than that, you need to go again and change it. So you carry out the fatigue analysis primarily to find out what is the damage and then coming back to the fatigue life only. Right.
So is there any specific like diameter or something depending on the floater size or how big is it?
So that's what depending on the excursion only. For example, your watch circle basically says that what is the excursion, how much it can happen, right? For example, in case of a drilling, you don't want it to go beyond a particular distance because that will have an impact on the riser, drilling riser that you have, right? So all these things are no straight answers. So it is like
Dependent on depth, it varies, something like that, the floaters.
see, anchor circle will definitely, we saw that, right? We saw so this is how it is. So if in case of a shallow waters, the anchor radius to depth will be a higher number, whereas in case of a deeper water, right, it is not. It is equivalent to 1. So this is for your anchor circle. For watch circle, you can tune it. For example, if I am going to increase the pretension value, then your excursion will also get limited, correct or not? Correct or not? If you are going to increase your pretension, the excursion will also get limited, right? So all these things as a trade-off between the items. So if your pretension is going to increase, the line length on the seabed will come down, right? Correct or not? If you are going to increase the pretension, your line length on the seabed will come down, which means that on the end B, which is the anchor point, there will be some loading coming up now. If you are going to have a very few meters on the seabed, let us take 300 meters, 400 meters on the seabed. So then that load will not be transferred to the anchor. So it is always safe, because when your floater moves, that much chain it has to be lifted up, right? That will again act down, that will give the restoring force for your floater. Because if you want to move it, you understand the point, right? When your floater excurses, it has to lift the mooring line, right? Now it is, since it is lifted, it is in suspension now, correct? So that will try to act down, the self weight will try to act down, and that will again bring back your floater to the initial point. Okay, so now we'll use the board. Okay, so just to make it little interactive, we'll do the derivation. So now, if some inputs are given to you, how to trace the catenary shape, right? What will be your top tension? On a thumb rule, we can say that what is the water depth multiplied by some catenary factor, right? Multiplied by its weight per meter, you will get what is the top tension. Is that right? Correct or not? If this is your height, what we told? So let us take the weight of your line is 10 kg per meter. Fine. The weight of your line is 10 kg per meter, which is in the submerged case, submerged weight. Basically, you can write it as WS or W, right? Fine. So now let us take this water depth. You know at what site you are going to install it. Is that right? Generally, when you go for a mooring installation, you actually know where you are going to install it, and how much line you are going to leave it, how much line you are going to release from your end, right? A person is standing here, right? He is going to release the mooring line. He knows how much line I am leaving it, right? So now let us take the total length. The total length as some 300 or 300 meters. So water depth is 200 meters, sir. So it has to be, of course, more than that, right? Okay. So now you dropped your anchor somewhere here. Then you have this connection all the way to your. So let us take somewhere here. The connection is inside, right, on the sea surface itself. So now you know where exactly you dropped your anchor also, correct? As a person who goes for installation, he knows I put an anchor here, I moved this much distance, right? So this distance also is known to me. Let us take this as x, right? So let us take around 150 meters or 100 meters, right? So let us increase it to 350, right, for safety. Fine. So now you know you have certain inputs, right? The question is how to get the proper or exact top tension here, and if somebody wants a top tension or somebody wants to know what is the tension along the line, how to get it, right? On a simple thumb rule you can get it. Basically what we said, 200 into multiplied with some catenary factor into 10, basically kg per meter, right? So this is in meter. So you will get it in what is the tension at that particular point. That's what we said. But if I want to trace this shape now, so this is basically at some x comma y, right? So let us take x1, y1, this is xn comma yn. If I want to trace this shape, how to get it? You get the point, right? Some inputs are given to you, whether you will be able to trace the shape, that's a question, right? Now we need to have some equations, then only we will be able to get it, right? First question. So now you have a physical problem with some inputs. Now I want to convert it to a mathematical sense, but I actually don't know how to get it. As of now, I don't know. So now to get it, let us try to take a very small element and try to do the force balance. So that's what you did, right? Fluid mechanics all the time. Whenever you want something, you take a very small element and you try to do all the force balances, try to come with some expression, right? Then you will have some equations based on which you will be able to get some reasonable inferences with the output. Okay, so now we told it is a line element, right? Basically, for example, what are the chain you are wearing, right? It will just collapse itself, right, in your hand. Is that right? It is not having any bending stiffness, right? But then when you try to apply some load, you will be able to apply it and it will resist for some time. For a gold chain, if you apply, it will go away. But for other thing, if you apply, it will take up the load, correct? So you will have some axial stiffness, but then the bending stiffness is nearly zero because it is collapsing in your hand, correct? Okay. So now let us try to do the force balance for this very small element. Try to come up with some equation which will be applicable throughout the line, and then try to plug in these data, right? Right? And then see whether we are able to trace the shape or not. Okay. So now let us take a very small element. In the zoomed view I have written it, right? So let us take this as end A, end B. I am going to have this as end A, end B, right? So now this point, right? And this is a small element we told, ds. Is that correct? Correct or not? ds. And now at this point, because it's somewhere in the middle only we have taken, is that correct? So that will have some tension here, correct? And this force we can resolve it, horizontal force and vertical force I can take, is that correct? The same way at this particular point as well, but then here TV plus dTV, because that small element, because at the top, correct or not? So you will have a TV plus an incremental vertical tension. When we say D, it is basically an incremental tension, incremental value. The D is basically a small element, right? For that small, what is the incremental happening, right? So here the TH will be same as the TH. Why? The TH whatever you have here is equivalent to the TH here. Why? If there is a difference in the horizontal forces, horizontal tension, it will move away, correct? So you are sitting in place, what are the load, what are the environmental load acting on the right side is equivalent to the left side, that is why you are staying in the place, right? The same way here also. So this TH will be same as this TH, whereas for this TV it will be TV plus dTV, because if you are just lifting a line, for example you start lifting it, right? So here whatever you see at the bottom, at the top, it will be different, right? The same procedure. Okay, so now you, for this small element there will be a load acting downward, correct or not? We told it W, correct? So this will be multiplied with the ds, that will be the net load acting downward, is that correct? So W into ds. So now let us do the force balance for this, right? So TV plus dTV equal to TV plus W into ds, is that correct? The net vertical activities, correct? So this TV will be gone, so dTV you are getting as W into ds, is that right, sir? Okay, so now what else we can do? So this is a very small element we told, correct? So let us take this as a dy, this as a dx, right? So let us try to, what is how to go to down, so I can write it down, it will not be continuous. Okay, so okay, fine. So ds, I can write it as dx square plus dy square for a very small item. Is that correct? Correct or not? Again I will summarize. So you have a floating body, a mooring line is connected, one end is connected to the vessel, the other end is connected to the seabed, and few meters on the seabed, right? So this particular point is the touchdown point. I think we forgot to write, so let us write it, touchdown point. So basically if you are going to lift it, this particular point is the touchdown point. After that few meters on the seabed, right? This is your fairlead, right? This is your anchor point, right? So now in order to solve this problem with, because you have been given with some inputs, so we are trying to trace the catenary shape. So to do that we need some equations. In order to get that we have taken a very small element, we try to do the force balance. That is what we have been attempting all this time, right? So now since we taken a very small element, we have taken, okay, oh this is okay, okay, good. So ds square equal to dx square plus dy square I can write, correct? So now what else we can do with this? What else we can try to get? So now can I write it this way? Because I need some expression, then only I can solve it. So I need some y as a function of x or something. So which as of now I don't know. I am trying to do the force balance for a small element, try to see is there any rearrangement can be done. That is what we are attempting all the time. So dy by dx whole square, I can write it like this, is it correct? We did nothing, just divide by dx square throughout, correct? Okay, so at this particular point you have some theta, correct? Is that right? So this theta is equivalent to this theta also, correct sir? Okay, so now we can write tan theta equal to dy by dx, right, which is also equivalent to Tv by Th. Is that correct? Correct or not? Tan theta equal to dy by dx, tan theta equal to this Tv by Th, correct? So now this dy by dx you can write it as y dash, right sir? So Tv by Th, correct? Okay, so now we have some other item also here, dTv equal to w into ds. So we need to bring in, you have different items which is segregated, let us try to combine them to get some expression. That is the idea. The whole idea is that you will have some equation y as a function of x which you don't know, you are trying to find out based on a simple force balance for a small element, correct? So now can we differentiate this one so that I can bring in this dTv component in this one? So you can see here, right? So I can bring in this dTv component in this one. So what we can do? If I differentiate, what will happen? Y double dash, right? Correct or not? So here this Th is constant, do you agree? Because the Th here is equivalent to Th here also, right? Correct sir? So I can write it as dTv, correct, by dx. So now this dTv is equivalent to w into ds, correct or not? This dTv I am bringing it from here, fine, by Th into dx, right? We did nothing, we have just taken a very small element, try to do the force balance, try to establish some relations, trying to mix them up to get some expression. That is what we are attempting as of now, right? Oh, okay, sorry, I think okay, it's moved away. Okay, fine. Okay, so then w by Th, let us write it again, Th into ds by dx, y double dash. So now let us give some name for this Th, because Th is known to you, but w is known to you, Th is unknown to you. As of now you don't know Th, right? Horizontal force you don't know what is actually happening, right? So Th is an unknown, Th an unknown, right? Whereas w is known to you, it is a known quantity, right? So now let A equal to Th by w. So some understanding we are going to bring in. So we are bringing a new term, A equal to Th by w. So now this basically becomes y double dash equal to 1 by A ds by dx, right? The same thing, no change. So Th by w I have written as A and I have simply retained it, right? So now let us try to see, now you have something for y double dash and some relation here again. So ds by dx again you have. So this ds by dx you can write it as root of 1 plus y dash whole square. Is it right? Yes. We can write correct. So this dx, so you have ds by dx y double dash into A. Is that correct sir? So now can we combine these two things? Right? So now let us try to plug it here. So y double dash into A equal to root of 1 plus y dash whole square, right? See, it started with nothing basically. You have been given with some input. Since you don't know how to trace the shape, you took a very small element, try to do some force balances, then try to combine different items that comes in picture. Finally you are getting some differential equation part now, right? Second order differential equation, slowly pitching in. See, as I started with nothing, but then you are ending up something of some equation. But then how to solve it again? That's a question now. See, finally as an engineer you should be able to say, so this will be the position at this particular arc length, right? You should have the idea what the tool actually does, right? If time permits, we can also actually do it in some sophisticated tool, arc of flex, and then see whether we are also getting the same values that what we solve in the class, right? Okay, so now you got this expression y double dash, right, into a, so we can write it as 1 by a root of 1 plus y dash whole square, right, or we can just group them, or we can write it as, now we need to solve this equation, correct sir? We need to solve this expression to get the solution. Basically you are interested in y only, but now it is in the second order, right? You need to get an y as a function of x. Okay, so now this y double dash by, let us try to group them, 1 plus y dash whole square equal to 1 by a. Is that correct? So what you have to do now? Integrate. Correct or not? You have a second order differential, now you have to integrate to get the expression for y. Correct? So now let us integrate it. Correct? So this is basically, I mean we will not get into how this sine hyperbolic terms are coming, but then we will directly write. So is it sine hyperbolic inverse or sine hyperbolic value? What is the value? Inverse, sure? Okay, sine hyperbolic inverse of y, is it? So this will be x by a plus c1, correct, some constant. So now we need to eliminate this constant. We don't know as of now. Generally how we eliminate constants? With some boundary conditions, right? See, you had a physical problem, you converted to a mathematical sense, you are having some headache now with solving multiple items coming up, then you are trying to resolve it now, you ended up getting second order, now you are trying to break down to a y as a function of some x, are we getting or not, right? Right? So now let us get back for the boundary condition. So at this point, so let us for ease, let us try to have the origin here at this location. Let us have our origin here. Fine, sir. So at this particular point, touchdown point, x equal to 0, correct or not? The small x, let us take small x. This is a capital X. From here to the point, it is the small x. Fine. At x equal to 0, y is also 0, correct? See, not necessarily you should have the coordinate system there. Sir, why should I have my coordinate system there? It's always a question, correct? You are free to move around, but accordingly you should take your boundary condition values also, correct? So this is easy for me because at the touchdown point my x is 0, y is 0, y dash everything is 0, s is 0, everything is 0, correct? Okay, so now considering that at x equal to 0, y is 0, is that right, sir? So now let us write the expression y equal to sine hyperbolic of x by a plus c1, correct? Correct or not? Just the same thing I have written it this way, that's all. Y dash, right? Now y only, okay, fine. Hey, is this a y dash or y? Y dash, is it? Y dash, okay, fine, okay, this is y dash. Okay, so when x equal to 0, y is also 0. So which will give us c1 equal to 0. Is that correct? So this will give me y dash equal to sine hyperbolic x by a. Is that correct, sir? Right? Okay, but then I am not interested in y dash, I am interested in the expression for y. So as for each value of x, what will be the value of y, right? Okay, so now what again we have to do? Again we have to integrate, right? Again we will integrate. So if you integrate, you will end up getting y on the left side, on the right side sine hyperbolic integration cos hyperbolic x by a by 1 by a, is it? Correct or not? By 1 by a plus some constant again, now c2, let us have c2. So now this is the expression actually I am looking for, right? Some for some value of x, whether we are getting something or not, right? So now again we have to eliminate. So at x equal to 0, again at x equal to 0, y is a 0, right? So if you put y equal to 0, cos hyperbolic of 0, this becomes 1, right? Plus c2, is that correct, sir? So now c2 equal to minus a, right? So now y equal to a cos hyperbolic x by a minus a. So this will be the final expression I am getting, correct? So a I can take it out, cos hyperbolic of x by a minus 1. So this is the expression that we are looking, but whether you will be able to solve it alone, you cannot do, because a is basically containing th by w. W is known to me, but th is unknown to me again. See this expression, you have an expression, but you cannot solve it with just this expression, right? You have one more unknown there, right? You have x unknown, you have th also unknown, two unknowns are there, right? So you need to have additional equation, right? Is it boring or okay, occupied? Okay. See, finally, I mean, my aim is that as an engineer, it's not just you see it, use some tool, but you should be able to calculate it. You should be able to do hand calculation, do your own stuff, right? That's always a better move. Okay, so now you have this expression. Now we need one more expression, right? Because there are two unknowns here. See, if you have two equations, two unknowns, good to go. You can solve the problem nicely. But then you have a single expression with two unknowns here. X is unknown, x is unknown, x is unknown, th is also unknown. Both are unknowns. So you need one more equation. As of now, you got only one equation. You need additional equation to solve the problem, sir. You cannot solve it as such. Correct? See, the problem was very simple. You know how much line, what is the weight, everything. But then you are unable to say exactly how much length will be on the seabed. What will be the shape of it. A simple problem turned out to be very complex as you started moving it. Correct? But then we started discussing for a discrete element, then you are ended up having some expression, but then still it is not complete. As of now, the problem is not complete. You need to have additional equation. That's what we are saying. Correct? So now let us see whether we are able to get some expression for S. For S. So what is the expression for y dash we had? For y dash. Where is there? Y dash equal to sine hyperbolic, right? Okay. So y dash, okay, so y dash, so we have, okay, I think we will write it bottom only. So now we are looking for some expression for S basically, right? Because that is the length which is suspended, right? So again, to draw the figure, so you have a floating structure. So now let us take, you are making some connection. So this length, okay, I think I made, okay, let us take it. So from this point to this point is basically your S, the suspended length, right? What are the length on the seabed? Let us name it as S naught. Let us name it, right? So your total length is basically S naught plus S. Is that right? I can write like that, right? From this point to where the fair lead connection, that what we call it as a capital X, correct? So now, in order to solve this problem, you should know what is the value of TH, then only you can actually solve, right? But you know what is the value of L, because that is given. You know how much you have left it, right, in the sea. You actually know how much length is dropped in the sea. That length you know, because some inputs are there for you. So now we need to have some expression for S, right? So from which expression can we get that? From which expression can we get it? Expression for S. See y dash, see you can take this expression, since you know the value of y, you can plug it this value, that is a one way to do, right? Is there any other easy way to solve the problem? Can we get something else easy? What else we can do, sir? You get the point, right? We have two unknowns, we got only one expression, we need additional expression to solve the problem. That's a point. How to get the additional expression? Moment equation. Why? No, we did not, we have just taken what is the forces acting at either ends of the discrete element only. We did not go for any of, that's what we told, right? It is not having any bending stiffness at all. So it is just collapsing. So there is no stiffness offered from the right? So that and all is not coming in picture. Correct? So now we are looking for some expression for S. How to get it? So if you actually take this expression wherein you have y double dash into a equal to ds by dx, if you integrate it, you will be getting some expression for S as well. Is that right? So now if you plug the value of y, this expression of y in that above equation, so you will get the expression of s. So s basically ends up with how to get it easily, ds by y dash into a equal to ds by dx, right? Right? Okay, so I think I can plug in this y dash value also here, is that correct? So root of 1 plus y dash, what is the expression you got? Sin hyperbolic x by a, right? So I can write sin hyperbolic x by a, right, square ds by dx. If I integrate this one, I will be getting the expression for s, is that correct? So there are multiple ways in which you can get, either you can do the double integration for y and use this expression, right, or use the other equation to get the expression for s, right. So finally you will have something of this. What is the expression you will get? I think is it the a sin hyperbolic x by a something you will get. Please check whether you are getting this one. Please check. Fine. See, you need to have additional expression to solve the problem. That is what we are discussing, right? So finally you will be ending up getting an equation for s as well. So now here you have one equation, here you have additional equation, right? These two equations has to be solved together. So a system of nonlinear algebraic equations has turned up now, right? You started with nothing, but then finally you ended up having a nonlinear algebraic equation. The problem with this is that you cannot solve the problem straightforward. You need to adopt some Newton-Raphson method to solve it, right? See, an easy problem looks easy, I mean it looks easy, but actually not easy when it comes to the real solving for a simple catenary for a single line, right? But then now if you have a mooring, some kind of a buoy attached, for example, I am attaching a buoy, a catenary line was there. If I am going to attach some kind of a buoy here, the shape will change to something of this way, right? Then it becomes even more complex to solve. So you will have one catenary, you have second catenary, you have third catenary. So 3 catenaries. So you will have a lot of unknowns now, and accordingly you have to set up the equations to solve the problem, right? So that, I mean, I just to feel it is not that easy when it as it looks, right? When you use a tool, it's always nice to run through, but when you actually solve it, so okay, now let us get back here. Okay, so this is what for a simple MATLAB program is written. Actually I don't want to get in this Newton-Raphson, again it will take another 45 minutes at least to run. If you are happy to sit, I am happy to go, but you will drain away, right? If anybody is interested, we can sit and continue. See, finally I wrote a MATLAB code to check out, so finally it ended up getting this outcome. So similarly for your moorings, again mooring line with the buoy. So now this is with the buoy. So in order to reduce the top tension, when a buoy is added, this is all without any environmental loads. You see the complexity. Without any external environmental load, the problem is not that simple. But when you actually take in the environmental loads also in place, how to solve it? That's a question now, right? That will again go as a big module. So if you are able to solve that, then you are actually developed a tool, correct or not? If you are able to get as a function of time the response of each of the different discrete elements, the stations, then you actually solve the problem, right? So the complexity keeps mounting as you increase it from the simple, right, to a complex wherein as a function of time, if you want to incorporate the effect of the environmental loads also. So this is a very nice work that you can actually do for your PhDs also. So wherein if you are able to develop your own tool, that is much preferred, right? People who write their own codes, it is always go a long way, right? So I strongly encourage. So I will stop here for this. If anybody interested, maybe we can extend this, keep on going. It will go for hours. It will be nice also, but then you should also get involved in that. Then it becomes good. Okay, I'll stop here. If any other questions, if any questions are there, we can take up. Okay. If you are able to do the time domain analysis for this, right? As of now, we did not take the positions are moving. If that position fair lead is going to move, if I give some harmonic motion for that, then the response of as a function of time, each time these what we call as the stations, right? Then those things will also keep moving, right?
Very nice analysis. And I also want to point out there are some software that you can use. For example, Unreal, they develop more than that can do analysis, static, dynamic analysis. And recently, they also extended the work together with us to include the vortex-induced vibration. So, and there are some commercial software probably works better, like Aquaflex, right? This software is very popular for oil industry for this mooring analysis, and also Aquaflex. The software is pretty expensive, but they may give students for some special license arrangement like that. Okay, so that's what I want to point out. Right, you can use some tools to use that. Thank you.
These days we have a lot of sophisticated tools. You just think it will appear in front of you, but it will also create a lot of dummies, basically, right? So you should get in the math part that comes at the back end, so that, see, all the things we cannot code it, but then you can always go a few steps ahead in the direction to feel what it is actually, right? How it has been built up, right? So it's I encourage students always to write code. So not to bring something very great, but then you will march in the direction slowly over a period of time. You will land up there. Any question? Fine. Yeah, you have a question?
Sir, TH
Yes.
is a function of x, right?
Yes. No, TH and TH is an unknown, correct? Yes.
It is a function of x.
Yeah, it will be a function of x also. Yes, correct. No, TH will not. No, TH horizontal tension will be same only. Horizontal tension will not change.
Oh.
See, if some horizontal tension is going to change on your body, for example, then you will start drifting or you start moving in the direction. Correct?
That we don't.
Yes. TH is an unknown for you. And what is the length on the seabed is also an unknown to you. So basically S0 and TH is an unknown. You need to solve it, for which you have end up with two non-linear algebraic equations. So I actually wanted to do this Newton-Raphson part also, but then I see a lot of detachments from now. So I mean, if there is a good involvement, we can do that also, right? I mean, so then only you will be able to get this outcome.
It will be fine if you simply you go single Mooring line.
Yes, sir.
Mooring line
Right.
TH will be fluid speed.
Yes. Yes. So environmental load has to be taken care for that current. For example, you have a current load.
Right.
So then TH, the current load will add up to the horizontal tension.
And I want to point out that for the marine energy, ocean wave energy, this research and marine is often some part that significantly underestimated element. People pay a lot of attention to wave, buoy structure design, PTO design, and they didn't pay enough to the mooring system. Well, no system failed because of mooring. Okay, mooring design and it's mooring itself. There are a lot of very interesting dynamics. For example, here you put a pond or buoy. Some place you put a heavy mass.
Heavy mass as well, correct.
And some place you put some spring instead of just only chain. You put some nonlinear spring so that you can reduce the extreme load. And if some weather happen like that, nowadays with the time going on, PTO WEC system become better. People now pay attention to the mooring, right? You just imagine that way you do research in the tank, whatever your fish line will be fine, you wouldn't pay much attention to that. But if you put things in the ocean, and mooring is significantly important.
Yes.
Okay. So there are a lot of active research here, and recently we have one project, and in contract negotiation, and we put the spring mass inerter in the mooring chain, so that we can reduce the shock load, and at the same time provide some function of node estimation, right? there are also some research and they use machine learning to do the mooring design. And one particular researcher is Lars Jonghanin. He used to be in was in UK, now it's Polymos, okay, and he dedicated whole his academic life on the mooring system design. Okay, so as there are a lot of good things we can do, and I would say now is become more and more important. Yeah. Thank you.
Thank you. Yes.
We have induced vibration.
Mhm.
Vibration. So it's a better lifting effect of the moorings.
Yes. So, for example, if you have any floating body, if it is going to respond to the wave, that load is going to be transferred to your fairlead. Then you will have some compressive wave which will be traveling from your fairlead to your part, right? So then it will also have the damping effects as it travels from, right? So for example, you have something vibrating, and if you put your hand there, it will quickly stop, right? So the same thing, the damping effects also will happen as it travels from the top to the bottom. So we need to take all those things in consideration when we design. So if there are no other questions, we will close out. Thank you.